Are we ready? Are we ready to learn more rules to the game? That's the question that you need to ask yourself, because it doesn't really just stop at Edmonds reagent and carboxypeptidase A and B. I wish it did, because that would make these problems so much simpler to solve. But the issue here is that Edmonds, which we saw in a previous video, and carboxypeptidase, so carboxypeptidase, we had two versions of that. We had an A version and a B version. Well, these are not the only reagents that we can use when it concerns primary protein sequence. So Edmonds, of course, gave us the first amino acid in the chain, and carboxypeptidase A gave us the last amino acid in the chain. The reason that we had two forms again, version A and version B, is because version A will cleave everything. So I'm going to put that here. It cleaves everything, except for two amino acids, and these were your basic amino acids of arginine and lysine. So carboxypeptidase A removes the last amino acid, but it will not do its job if there is a arginine or lysine at the last location. It just simply will not provide you a fragment. That's where carboxypeptidase B comes into the picture. And carboxypeptidase B only cleaves if there is a arginine or lysine at the very end of that amino acid chain. So we've discussed these already. This happened, a couple of videos back before we even did our example problems in the past two videos. But this is a review of kind of where we've made it to at this point. So we've talked about Edmonds and we've talked about carboxypeptidase, A and B both. Okay, so now there's going to be some new reagents that we can throw in. And when I say reagents, I'm using it as a very loose term, and the reason is because these aren't simple stock solutions that you can make from a chemical compound like you've always done. These are actually, just like carboxypeptidases, they are actually enzymes. They are actually proteins that do the work on these proteins. So it's kind of strange that we're using a protein to cleave another protein up, but that's exactly how these things work. So these things are huge. Their structures are very large. Carboxypeptidase A, if you go back and take a look, we didn't do a structure for carboxypeptidase A. We didn't draw a structural compound like we would with benzene or toluene. I mean, we did it with Edmonds because Edmonds was a chemical reactant, but carboxypeptidase A was kind of a different story. We can't really draw a structure for that molecule. The same thing is going to happen with some of these others. These are really proteins that we are using to do a very specific job. So because of that, we simply just do not put in a structure. We talk about it. Maybe we'll show you a three-dimensional protein structure of what these things look like. But structure-wise, no, that's out of the picture. We just really want to know, what does it do? That's really all that we're after. So the first one that we're going to talk about is this thing called trypsin. So Trypsin, trypsin. Trypsin is another one of these proteins that do a specific job, and the role of trypsin is that it cleaves arginine and lysine. So you're probably thinking, well, we've got carboxypeptidase A that does that. Well, that's true. But carboxypeptidase A looks at the last amino acid of the chain. That's how this is different. So carboxypeptidase will only look at the end amino acid and cleave that ending amino acid. The good thing with trypsin is that it does cleave arginine or lysine, but this can be anywhere in the molecule, and more specifically, we're talking about in the middle of the protein chain. So when we take these long protein chains and kind of strand them out from front end to back end, N terminus to C terminus, Trypsin actually goes through that chain, and it looks for arginine and lysine anywhere where it can find it. And it cleaves the arginine or lysine off into a fragment. So what we often say is that it cleaves on the right-hand side. So wherever arginine or lysine is found, it cleaves at that spot. I'll show you an example here in a minute so maybe you can understand it a little bit better. But it cleaves the right-hand side of that amino acid, and we get fragments that come off of that chain. That's how we get some of these fragments that we do. So that's the purpose of trypsin. It goes through, it cleaves arginine and lysine anywhere where it can find it. It doesn't have to be at the end of the chain like carboxypeptidase does. The next one is a modification of trypsin, and this is going to be called chymotrypsin. So CHYMO, and then the word trypsin comes after it. Chymotrypsin is really the same thing. It's another protein. It's going to scan the primary sequence of amino acids, and it cleaves the right-hand side of aromatics. So I'm going to put aromatic seeker here. So it looks for aromatics. And the aromatics, as we've discussed so far with our 20 amino acids, are phenylalanine, tyrosine, and tryptophan. So those are the three that chymotrypsin will look for. So again, you take this protein chain, you have an N-terminus and a C-terminus, and you have all of these amino acids that line up because of it. Chymotrypsin will go through and it will find any phenylalanine, tyrosine, or tryptophan, and it cleaves to the right-hand side of that. So we get fragments from this big, long chain of amino acids. You got to think of these as a pair of scissors cutting a string. That's exactly what we're doing here. The string is the protein that we have just stretched out now. And these enzymes, the chymotrypsin, the trypsin, the carboxypeptidase, the Edmonds, these are the scissors. And they're going in and they're cutting the string up into different pieces. So this is the way that you have to think about this primary sequencing rule that we have to go through with the lecture. So there's trypsin and chymotrypsin. We have a third one. And this third one is going to be another kind of protein like trypsin and chymotrypsin, and this is called elastase. Elastase, elastase. So elastase is going to go through the same thing. It looks for the smallest amino acids, and the smallest amino acids, so that's what I'm going to put here. It looks for the smallest. And the smallest amino acids that it will look for, that it will cleave, it cleaves on the right-hand side again. Well, the smallest amino acids, as you would guess, would be glycine, of course. That's our simplest. We have alanine. Alanine is very simple. It's just a methyl group. Serine and valine will also be included. So these are the 4 amino acids that it will look for, and it will go through and it will cleave on the right-hand side of these amino acids if they're there in the protein itself. Okay, finally we have a fourth one, and this fourth one is going to be called thermolysin. So Thermolysin, thermolysin. And thermolysin will take a look at specific amino acids. What are these amino acids? Well, it's isoleucine, methionine, phenylalanine, tryptophan, tyrosine, and valine. And thermolysin will again cleave on the right-hand side of any of those amino acids that are listed there for the list. Okay, now we're not going to talk about the mechanism at which these things do their job. We just know that these things do their job, and we know that they target specific amino acids in the chain, and they begin to fragment up this chain for us. So, what that means is that you're going to have to memorize, yeah, I said it again, you're going to have to memorize these reagents. You're going to have to memorize these specific proteins that do a job, and that job is to cut the protein up. Now there's one more here that we have not listed, and that goes with Edmonds reagent. And the alternative up here at the top for Edmonds is cyanogen bromide. And I really say alternative, but I really should describe that a little bit different. So let's come down here and let's list it by itself. And let's take a look at cyanogen bromide. So cyanogen bromide. Cyanogen bromide is very similar to Edmonds reagent in the fact that it is a chemical. It is a true blue organic kind of molecule that, just like Edmonds, can go in without a problem and do a specific job without any issues at all, because it is reactant based. It is not protein based. It doesn't have to rely on shapes of the amino acids to do the job. It relies on basics of chemistry to do the job. So cyanogen bromide will go through and it cleaves on the right hand side of methionine. So it only looks for methionine, and that is it. And once it finds methionine, it cleaves it at that spot, and we get some fragmentations that happen because of it. So, like Edmonds, cyanogen bromide is very specific. It will do its job almost every single time. Why do I want to say that? Why is that such an importance? That's because that carboxypeptidase A and B, trypsin, chymotrypsin, elastase, and thermolysin, they are all proteins. They are looking for shapes. They are looking for structure, and that's how they do their job. They go in and they do their job because the seat fits. Just like Goldilocks, the bed feels really good. This one's too hard, this one's too soft, this one's exactly what I'm looking for. That's what carboxypeptidase A, trypsin, and all the others, that's what they're doing. They're Goldilockses. They go into these houses and they kind of look at their options, and they want the right type of bed with the right firmness, with the right size, and that way they can be happy and they can go in and they do their job. Edmonds and cyanogen bromide, they're not specific, and that means, or they're not particular. So basically what that means is that they will go in and go to sleep no matter what. They don't care what kind of bed is in that house. If it's a bed of coal, they don't really care, because they're going to go and they're going to sit on it and they're going to go to sleep. So Edmonds and cyanogen bromide, they don't really give us a problem. However, carboxypeptidase A, B, trypsin, chymotrypsin, elastase, and thermolysin, all of these have problems that we associate with them, and the problem here is proline. Proline was that weird amino acid that kind of wrapped around on itself, right? And it hooked up the alpha carbon with the nitrogen of the amino group. And when that begins to happen, proline begins to take a kink in the actual chain itself. And depending on what's around it, we have issues when it concerns these carboxypeptidases and everything else that's below. So if there's proline at the hydrolysis site, that's what we call the place that we cut the string, then the cleavage or the cut will not happen. Okay, that I can't say that enough. So if proline is there, the cut will not happen with any of these carboxypeptidases, trypsins, or anything else below. So you've got to look out for proline. If you see proline at that location, then you know that there's going to be an issue, and you know that typically no cleavage is going to happen because of it. However, cyanogen bromide and Edmonds, they don't really care. They're not looking for specific shapes. They're looking for types of bonding. So this is just basic organic chemistry that Edmonds and cyanogen bromide will release. Now, we have a particular name that we like to use for carboxypeptidase A and B. They look at the last amino acid. So because of that, we have a term, and this term is called an Exo Peptidase. And you got to think of XO as on the outside. And then trypsin, chymotrypsin, elastase, and thermolysin. All four of these are called endopeptidase. And the reason that we call them endopeptidases is because they cleave on the inside of the amino acid chain. So XO, only the outer last amino acid will it target. and endo, meaning anything on the inside of the amino acid chain, will be fair game. So in the next video, we're going to be looking at some example problems using the exo and endo peptidases.